Welcome to the Explainer. Today, we're pulling back the curtain on artificial intelligence. How do you actually teach a machine to think? Well, you might be surprised to hear that it doesn't start with some insanely complex algorithm. Nope, it all starts with something way simpler: puzzles.
So think about it. How does a machine make that leap from just following a list of commands to actually coming up with a strategy? The real challenge, the core of it, isn't just about throwing more computing power at it. It's about teaching it how to see, how to understand the problem in the first place.
And the secret to doing that is you teach it how to play. Seriously, AI developers build this kind of digital gym, a training ground filled with what they call toy problems. Now, don't let the name fool you. These aren't just games. They're the fundamental exercises that build the logical muscles an AI needs to solve problems out in the real world.
All right, let's get into it. Before an AI can even begin to solve something, it needs to know the rules of the game, like perfectly. This whole process is called problem formulation, and it's all about translating a challenge into a language a machine can actually understand and work with.
Pretty much every solvable problem can be broken down like this. You've got your initial state, which is basically where are we starting? Then a set of possible actions, or, what moves can we make? The transition model predicts what the board looks like after each move. The goal test is constantly asking, are we there yet? Have we won? And finally, the path cost. That's just a score. It tells the AI how efficient its solution turned out to be. Let's make it simple. Think of a road trip. Your goal is to get from Arad to Bucharest. The initial state? You're in Arad. The actions? Driving to the next city on the map. The goal test is just asking, am I in Bucharest? And the path cost? Well, that's the total mileage. All of a sudden, this vague idea becomes a neat, structured puzzle that a machine can actually get its head around.
Okay, so let's put this framework to the test. Our first challenge, the AIT puzzle. This is a classic, a toy problem designed specifically to test an AI's ability to find the most efficient path to a solution. We call this skill pathfinding. So, for the AI, it's really straightforward. The jumbled grid is the initial state. Its only possible action is to slide one tile into that one blank space. The goal is a perfectly ordered grid 1 through 8, and every single move it makes adds 1 point to its path cost. The challenge is dead simple. Solve the puzzle in the fewest moves possible.
But here's the kicker. Even for this simple little 3x3 grid, there are more than 180,000 unique arrangements. That's the entire search space the AI has to dig through to find that one perfect path. It's a big number for sure, but for a modern AI, totally manageable.
Now let's move on to our next puzzle, the 8 queens problem. This one needs a completely different way of thinking. See, it's not about finding a path from A to B, it's about satisfying a really strict set of rules. Researchers call this a constraint satisfaction problem. The rule itself sounds simple enough, right? Just place 8 queens on a standard chessboard so that none of them can attack each other. That means no 2 queens can be on the same row, same column, or even the same diagonal. But the really fascinating part isn't just finding a solution, it's how we decide to frame the problem for the AI. You could actually formulate this in 2 very different ways. First, there's the brute force method. Just start plopping queens down on any of the 64 squares and see what sticks. Or, you could use the smart approach, add queens 1 column at a time, but, and this is key, only in squares that aren't already under attack. It seems like a tiny little tweak in logic, but the difference it makes is absolutely staggering. With that first brute force method, the number of possibilities the AI would have to check is, well, it's a number with 14 zeros after it. We're talking hundreds of trillions of possibilities. That's not just big, it's computationally absurd. You just can't solve a problem that way. It's a dead end.
But with that second, smarter formulation, the number of possibilities to check plummets from hundreds of trillions down to just over 2,000. The problem goes from basically impossible to totally solvable, like in a fraction of a second.
And that right there is the crucial point. Building truly intelligent systems isn't just about raw computing power. It's about teaching them to think efficiently. How you frame the challenge, how you set up the problem, is everything.
This is exactly why these toy problems are so important. They are the training exercises, the practice drills that prepare an AI to take on huge,
messy, real-world challenges.
And this logic, it's directly transferable. The pathfinding skills from the AIT puzzle, that helps power robot navigation in a warehouse or even your car's GPS. And the constraint satisfaction from the 8 queens problem, that's essential for designing the ridiculously complex microchips in our phones and planning out automated assembly lines in factories.
So, when you boil it all down, AI problem solving isn't magic. It's really just the art of taking a messy, complex world and simplifying it into a defined puzzle, one with a clear starting point, clear moves, and a clear goal.
The key to all of this is a single concept: abstraction. It's the art of stripping away all the irrelevant details to focus only on what truly matters. Because let's be honest, without this ability to create useful abstractions, any intelligent agent would be completely, utterly swamped by the chaos of the real world.
These foundational skills, the ones learned from our simple games, are exactly what allows AI to start taking on some of humanity's biggest, most complex questions. The puzzles are just getting bigger, the stakes are getting higher, and it's really anyone's guess what the next move will be. Thanks for tuning in to The Explainer.